Welcome back. We will see here shift register. Shift register. There are various types of shift registers. So, for example, you have left shift register, okay, and the right shift register. There is a something called universal shift register. So, shift register. Like that, various registers are there further. Okay. So let's talk about the left shift register. So in left shift register, let's say we are saying 4-bit register. Here we have total 4 flip-flops because a group of flip-flops nothing but register. So that's why this flip-flop also called 1-bit register. So now here, let's say the position of this flip-flop is 3 and this flip-flop is 2. This is 1. This is 0. Okay. Now, if you are performing left shift, meaning from this end to this end, data will be moving like this. So, whatever you are going to give here, that is called data in. And this data in is passing through these flip-flops. And reaching to this output port here. Let's say that output is D out. Now, I have, let us say, bit 1. Okay. The moment when we apply the clock here, let's say all of this flip-flop being connected to a clock. Say clock. All these flip-flops being connected to the common clock. Now, when clock is triggered, let's say it is working at positive edge clock. When clock is triggered, previously, let's say all these have got 0 here on their output, 0, and this is 0, and this is 0. Okay, previously, before this clock, before this clock occurrence, let us say previously, all of these flip-flops have got 0, 0, 0. Now, when this clock has come, you are applying D in as a 1. So, where this 1 will be appearing on the first clock here. Okay, 1. So, remaining will be 0. Remaining will be 0 means this 1 being pushed here and this 0 actually been pushed here. And this 0 being pushed here. And this 0 being pushed here. And since this D out is connected to this last flip-flop here, this value will be 0. Now, this is happening at the first clock. When I apply the second clock, now what is happening is this 1. Let's say here what is coming at this first flip-flop depends upon what is the data in now. Further, after this 1, you may have again 0, you may have 1. So those data bits will be pushed to the first flip-flop, but I am concentrating on the first. At this first clock, what I have done is I have pushed my D in. When I come to the second clock, this D in I am concentrating. This D in is pushed here on the second clock. So here it is 1. Now when I apply the third clock, So here, when third clock been applied, this D in is pushed here. Okay. Now when you apply the fourth clock, this D in been pushed here. So it means upon fourth clock, your D out is going to get 1. So from there on, whatever the D in is there, that is going to appear from fifth clock onwards. Because, the moment this one been, pushed here to the, MSB side flip-flops here. So whatever the other data bits are there, they are following that bit, right? So it means what? After fifth clock, after fourth clock, T out continuously going to get whatever the subsequent data that had been followed this very first data bit. So those bits will be appearing. Only the very first appearance, whatever the D in we have given, will be appearing at the fourth clock. But after that, whatever the D in you give, that will be continuously appearing without this wait. That is 3 clock wait. This 3 clock wait we have done only for the first data. But for the second data bit, we don't need to wait this 3 clock wait. It keep coming like, yeah, of course it has passed all of these 3 flip-flops, but because of the very first data will keep moving, it had followed that. And then from fifth clock onwards, whatever the data bit that had been pushed into the D in here, so that is appearing without any this latency. All right. So now how do you model this one in Verilog HCL, this behavior? So it is a 4-bit register. We have to understand as I told you, what are the primary primary inputs, and we also have to understand what are our primary outputs. So what might be the primary input here? D in is one primary input. This is, let me take this one, where D in is one primary input. D out is another primary. D in is a primary input. D out is a primary output. Apart from that, we have this clock. Clock is a primary input. And to bring all these, registers to a known state, we need a reset. So we also need a reset. So let us put this reset asynchronous reset. Synchronous reset, asynchronous reset. So we have primary inputs. One is DIN, the other is clock, the other is reset. 3 input pins and 1 output pin, that is D out. So let's see how we can model this one. Before we go for the Verilog coding, one more thing that you have to understand here is, see, when you are, the very first clock has come, D in been moved here, LSB side here. And at that time, what is happening actually? All of these bits that are here, 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 they moved towards MSB side right here. So it means what? This, if you're considering as a second, and this is first one, and this is 0th one, 2, 1, 0. They have taken a position of this 3, 2, 1, right? Now at this vacant position, D in has actually taken place. This D in, whatever the D in you have given here. So it means what? If you're considering it as a 4-bit register, Q, Q been updated with the Q of 2:0. Yes or no? 2:0. See, this is the second bit. This is the first bit. This is the zeroth. They are actually all this three together been moved towards MSB side. And then in LSB position, DN has come. So we can concatenate like this. I repeat again. Pay attention here. You have total 4 bits, right? This is the fourth bit. This is the third bit. This is the second bit. This is the first bit. But what is the custom in digital logic? It's starting from 0, right? This is 0, this is 1, this is 2, this is 3. When you are performing left shift, that is moving from this end to this end. So it means what? This 0 been moved here, this 1 been moved here, this 2 been moved here. So it means every time this happens, right? So it means whenever clock comes, this phenomena going to happen. Whenever there is a clock here, whenever you apply the clock, so this phenomena is going to happen. So it means what? If you call all of this, flip-flops as a queue, queue size is what? 4 bits. So queue of 2:0 will take this MSB positions here. I mean, left hand side, they will be moved. All this bits 2:10. This 2:10. This 2:10. They will be moving here, right? This position. So it means what we can do is Q is a 4-bit. To that, what we can assign is Q of this 2:0 position bits. And this compresses, I mean, Q of 2:0 means 3-bit, right? But it is left hand side, it is 4-bit. One more bit we require to put here. That is what comes here, that is data in. So that data in sits here. Now you concatenate this. So when you apply the first clock, this happens. When you apply the second clock, at that time, what happened? This D in actually taken position right here. Like again, the same thing will happen. Like you will be moving here. Q of again 2:0, then D in again. This is the new D in that comes here. By that time, here when second has come here, this D in actually in a Q of 0 position. No? So that Q of 0, 1, 2, they've been moved here. Making sense? This Q of 2:0 actually had gone into Q of 3:1. Okay, Q of 3:1 in that it had gone. Now what we are doing here is we are moving all these bits like Q of 0 bit, Q of 1 bit, Q of 2 bit. In Q of 0, we have already DN. DN been moved here already with this first one. Because Q of 0 is actually mapped to Q of 1 here. Yes or no? This then Dn is actually going to the Q of 0th position. Same happens again for subsequent clocks also. So that's how we move to the left-hand side. In case if you have doubt here, you please make a phone call or drop a comment. I will answer there. Let's go for the coding now. So as said earlier, we have to double click this model sync. Now click on this jump start, create a project. And our project name is Left Shift Register, LSR, browse. As I told already, in previous recordings, you have to have one folder created. So go to that folder. I have created this folder, lab demos. I'm going to that folder. Inside that, I'm creating another folder. Name is LSR, Left Shift Register. Select that folder. Okay. So that folder being selected here for the project location. Now, these two things default, you have to leave as it is. Click OK. Now create a new file. Name is LSR again, that is left shift register. And this is important. Add file as type is important. Select Verilog. Click OK. Now we need test bench also. So here you can see that been added LSR. Now create a test bench file. That is TB underscore LSR, left shift register. And this requires to be changed to Verilog. This add file as type, add file as type is a Verilog. Click OK. Now you can close. Now double click this LSR, double click this just TB underscore LSR. So here you can see the tabs here. So let's go to LSR. Let's start coding. Module. And this is LSR. Open the parenthesis. We have clock, we have reset, we have data in, and we have data out. Now, type declaration, input, clock, reset, the in. And here it is output, the out. Now, always, it is sequential circuit, so always at the rate pause edge clock. So we are working at positive edge clock, so pause edge clock. If multiple statements are there, begin and end is required. So now what is that you have to write? If reset. So I told this is asynchronous reset. So, but the coding, the way I have done here is a synchronous reset because whenever project occurs, then it comes into this block, always block. Then it checks the reset. It means it is becoming synchronous reset. I don't want synchronous reset. I want asynchronous reset and active high reset. In that case, what I have to do here is comma, put forward reset. So irrespective of your clock occurred or not, if if reset is changing from 0 to high or any other value to high, that is, let me get this one here. So your reset is some unknown value initially, we don't know what it is. But from that, it is moving to high, let's say. So at that time, this block will be triggered. Then it checks this reset is high. Obviously, since it is going high, like project is occurring, it will be high only. So then reset will happen. Irrespective of your clock. So that's how it is. So this becomes a synchronous reset now. So what I'm going to do is I need 4 flip-flops. So them I have to code like this in Verilog. Reg 3:0. Let's say Q it is. So here I am going to put Q as a 0. Else. So what I have to do, as I said here, I have to use concatenation operator and I have to take Q 2:0, this 3 bits, and move them to this 1 bit higher position. That's what I have done using this concatenation operator. Here, comma, then D in is sent to this LSB bit position here. Okay, using concatenation operator. Same thing I am going to model here. So else Q is assigned with the concatenation operator Q of 2 colon 0 comma D in. So that is what the logic is here. Okay. So this begin and is over. Now assign this D out will get data from the MSB, right? Here, if you see this one, this one is connected to the MSB. Here I already discussed. Here. This MSB is connected to this D out. So here MSB is Q of 3. So that completes our plot. And now what we have to do is save this file. Now go to the test bench. So I'll just copy this. These things are required there in the test bench. Copy, go to the test bench, backport, time scale, 1 nanosecond slash 1 PS, and then module TB underscore LSR, left shift register, and paste it here, whatever you have copied. But this one module, cut this and put after this input and out. And then after this name, you just put some instantiation name. About this instantiation name in previous recordings, I already spoken about that. And in test bench, this input will become reg. And this output will become wire. Now what I have to do, I have to generate the clock, all the initial, begin. I'm making my clock initially 0. In my reset also 0. Then I just close this. Dollar monitor, you please write. I already demonstrated that dollar monitor is to display in the console here. Try that. In case if you have any issues, you please ask. Always hash by clock negation of clock. This is to generate the clock with 10 time unit delay, 10 time unit period. Okay, because for for 5 time unit it is on, for 5 time unit it is off. So it means total 10 time unit is the clock period. So now what I'm going to do, initial begin hash 3. At that time, I'm making reset 1 and then waiting for the clock to occur. But since it is a synchronous reset, anytime you can make your reset high. You don't need to wait for the clock here. So, okay, in case this test bench will help you in case if it is synchronous reset also. So let me go with this. At the rate pause at clock. You actually, what I mean is you really don't need to wait for this. The moment when you have done this pause, reset high. So this is happening here. This is already happened. You don't need to wait for the pauses to occur in the test bench. Now what happens is this phenomena will happen. Okay. So here you don't need to wait, but I'm keeping this in case if you make this synchronous reset. By removing, if you remove this one from here, then it will become synchronous reset. So let's keep as it is. Now let us proceed. Now what we have to do, at some point of time we have to remove this reset. Otherwise, always we'll distracted this we want to see means we have to remove this reset high. So let's remove the reset high. Hash. I'm not waiting. I'm just removing up soon after the forward occurs. Then I am removing reset by making reset 0. So once I have done that, at the moment when I'm doing this one, I place this D in as a 1, beta in. Then I wait for the progress to occur. Control C, control. So now what I do, I just wait one time unit. I'll make my D in some different value, and then again I wait for the progress clock. This I will copy this entire thing, control C and control V. So D in I gave here 1, here 0, I'll be giving again 1. So now what I have to do, so as I said, 4 clocks are required here. This D in to appear on this output side, we need 4 clocks here. So it means here, this D in to appear, we have to wait 4 clock. This is 1 clock, this is the second clock, this is the third clock. So I have to have one more clock to see this D in on the out. But to see them also, I need additional clocks. So let's put 3 clocks. So without any further D in, simply 3 clocks. This is to see the data. I'll just copy this one. And then I can wait for some time, random time, and then you can stop your simulation, $stop. And then this begin needs to be closed. That is end. Once this begin is closed with the enclosure end, now what is left? This module needs to be enclosed with the end module. So that completes our test bench code. Now, what is that we have to do is we just compile this. Compile, see whether any errors here. So no errors. Now you go to simulate, start simulation. Try to locate this work folder and there's a plus sign here. Click on that. Select your test bench module. Click OK. Now wait for here sim tab to come. Library tab, project tab, sim tab. Once sim tab comes, right click on this module name, that is test bench module name, add wave. So now you can see signals being added here. You go to this and change this P to N because our scale is in nanosecond and increase depending upon your requirement is how many clocks that simulation time that is required. Here, if I roughly estimate here in the test bench, from the test bench, if I roughly estimate 1, 2, 3, 4, 5, 6, 7. 1 clock period is here 10. So 70, at least 70 clocks are required. So 100, okay, that is good. So 100 nanosecond is fine. Now run this simulation. So once simulation been run, you don't have here anything to display because we did not write $monitor. Now you click on this zoom full. Now you click this clock. Click here initially somewhere here, beginning, very beginning. Now here you can see find the next rising edge. Click on the next rising edge. So before that, we have to understand here, see this when reset is high. See, reset is high here. So irrespective of your clock edge, your D out is 0. Okay. So that is what asynchronous reset is. We don't depend on the clock. Now select the clock signal, select this one here. When clock is high, this D in is 1. Initially what we have given here. this D in, that is this D in. This D in is so this D in is expected actually upon fourth clock out in a output in the output. So this is the first clock, right? Second clock is click this second clock here. We can notice D out is still 0. Third clock, D out is still 0. Fourth clock, what is expected? Your D in 1 is expected here. So let's see why is that we are not getting D in 1 here. Uh, Let us go to the very beginning here. This is the first clock. At first clock, what you have D in 1. So this D in 1 is what expected on the fourth clock, upon fourth clock on the output. So this is the first clock, second clock, third clock, fourth clock. On fourth clock, we must get this D in on output. What we are getting here on fifth clock. So let us analyze that. Why is that happening? So this is reset, that is fine. When you come here, Dn is you are concatenating with the Q of 2:0. That is correct. Now Q of 3 is assigned to D out. So here in the test bench, this D in must have been even before the clock actually. That's why it is happening. So I'll tell the concept here. What is the concept? Our data must be available before the clock occurs. See, this is your clock. There is some concept called setup time and hold time. So if some data is there, let's say some data that must be available even before this clock edge. Okay. So here it must be stable, your data in this window. And it must be stable even after that edge occurs. So this is called setup time. And this is called hold time. So this is huge topic to discuss, but for now, setup and hold. Okay, we are actually violating that one here. We are actually waiting for the project's clock. Then this we are making this reset. Sorry, D in 1. So what we'll do is now we did this reset high at 3 nanoseconds, right? So after that, we will wait 1 nanosecond, one time unit, and then we will make our reset save so that we can start working with our design. At that time, I'll put this in there itself here. Now I'll remove this reset because reset I already made 0 here. Now this clock is also not required here. So now see, data is available even before this clock occurs. Okay. Now, after this clock occurrence, I am waiting for this time unit, one time. That is to maintain the hold time and setup time and hold time. This one. This window I am satisfying. Setup time and the hold time. Data must be stable at this clock edge. Okay, that is what I have done. This is before this clock itself. I kept this data in. After that clock edge, my data in is still stable till this, further one time unit, then I'm changing my data. So that way I have maintained my setup time and hold time. Now this clock will occur. Now again I maintain that hold time And then this, I change this data in, then this clock occurs. And then from there on, this is, I'm not going to change this data further. I'm just going to wait for another clock because this is the first clock. Fourth clock, I must see the data. This is here, first clock. So this is our second clock here. And this is third clock. And this is fourth clock. Here we must see the data. This data in must be appearing on the output. Now at fifth clock, here what appears is this 0 appears. This sixth clock, this 1 appears. So that I already discussed here. So it will like, by moving like that here, first clock, second clock, third clock, fourth clock, fifth clock, like that. From there on, data will continuously will appear. So let's save this and let us compile again. So successful. Now go to simulate, start simulation. Here locate the work folder, expand this one, select the test bench module name, click OK. Now here ensure that this is nanosecond NS, then click this one. But before clicking this one, you have to add two waveform window the signals. So signals been added to the waveform window. Now run. So now here in the tab, select the waveform window. This is wave. There you go for zoom full. Now select your clock. Then you go for this find next rising edge. So, but before you do that, you have to click once for getting this, cursor. Okay. That's why when without cursor, there cannot move the cursor. This error is a message here. So now we have the cursor here placed. Now click this next rising edge. So now you can see, but this is pointing to the rising edge of the reset because the reset been selected here. So anyhow, if reset is high, irrespective of your clock, your output is 0. Now let us select the clock. Now click on this next rising edge. So next rising edge here, we have data in 1. So this 1 is what expected here upon the fourth clock. So this is the first clock, right? Second clock, this is 0. Third clock, this is 0. Fourth clock, this is 1. Now what is expected on the fifth clock? 0 is expected because in test bench, after first clock, when second clock comes, 0 is there. Now, this 0 will appear on the fifth clock. So here we are there at fourth clock now. If you click this one on the fifth, we are there on fourth clock. It's first, second, third, fourth positive edge. When you click, then you'll go to the fifth clock. There you will see the 0 here on the output. So that is 0. Now on the sixth clock, when you click this one you will see because the interest bench we have given here 1. This will appear on the sixth clock. So from there onwards, whatever data been given, it will appear like. Now 6 clock I'm clicking. So 1. So this is what left shift register is. Okay. Based on the similar logic, you can try actually right shift register. I hope you people will try. To close this simulation, you go to simulate and simulation. Then click yes. So you'll stay in the application, only simulation part being closed. Okay. So that's how it is. This can be treated as an experiment and there is a possibility of coming in external exam also. No one can have a claim that we did not do in the lab. How regular you people are to the lab, you know very well. So I have recorded this. You practice this and this will come in external exam. Okay. So I stop recording here.